Welcome to homework.
Okay, so problem 5 states that chemists use infrared absorption spectra to identify chemicals in a sample. In one sample, a chemist finds that light of wavelength 5.8 micrometers is absorbed when a molecule makes a transition from its ground harmonic oscillator level to its first excited level. Part A, find the energy of this transition. Okay, so the energy levels of a harmonic oscillator are given by E sub n is equal to n plus 1/2 h bar omega, where omega is equal to the square root of k prime over m, where k prime is the spring constant or the force constant of the restoring force, and m is the mass of the particle on the oscillator. Okay, so we're also given that the energy of a photon is, or the wavelength of the photon, I should say, is equal, that initiates a transition from the ground state. We're given is, let's call it E gamma, is, sorry, no, I shouldn't do that. I should say lambda is equal to 5.8 times 10 to the minus 6 meters, or 5.8 micrometers. All right, so now for part A, we need to figure out what the energy of the transition is. So the energy of so the transition energy from a ground state to any state is going to be equal to the energy of the photon that initiates it. So the energy of a photon is given by hc over its wavelength, which is equal to 6.626 times 10 to the minus 34 joule seconds times 3.00 times 10 to the 8th meters per second divided by this wavelength here, 5.8 times 10 to the minus. So this is 3.43 times 10 to the minus 20 joules, or 0.21 electron volts. So that's part A. So this is the energy of that transition. So it's the energy of the photon that causes the transition. So for part B asks, if the molecule can be treated as a harmonic oscillator with a mass 5.6 times 10 to the minus 26 kilograms, find the force constant. All right, so now we need to know that, okay, so we need to find the force constant. So we need to know this K prime here. So the delta E, the energy of a transition in a harmonic oscillator is from the ground state is given by E sub n minus E sub 0, which is equal to n plus 1/2 h bar omega minus 1/2 h bar omega, which is just equal to n h bar omega. And since the problem states that it's going to the first excited state, so n is equal to 1, so this is equal to h bar omega, which is equal to h bar times the square root of k prime over m. Okay, so the energy of, now we know the energy of this transition that we solved for in part A. So we'll put that, for now I'll just put delta E is equal to h bar square root of k prime over omega. We want to solve for k prime, so we square both sides. We get delta E squared over h bar squared is equal to k prime over m. go ahead and just do the whole solution there. So now we can plug in the numbers that we have. So that's going to be equal to 3.43 times 10 to the minus 20 joules squared divided by the mass of an electron. I'm sorry, not a mass of an electron, the mass that it gives us, these 5.6 times 10 to the minus 26 kilograms, which is a typical mass for an atom, a proton or a couple of protons. So that's kilograms times h bar squared, which is 1.055 times 10 to the minus 34 joule seconds squared. All right, so work through all of this. Oh, you know what? I made a mistake here in this. The mass is on top. Sorry about that. Delta E squared mass. So let's go ahead and move that. Let me get rid of that here. Let's go ahead and erase all of this just to rewrite this a little bit better. Okay, there we go. All right, so times the mass, which is 5.6 times 10 to the minus 26 kilograms divided by h bar squared, which is 1.055 times 10 to the minus 34 joule seconds squared. All right, working through all of this, you get an answer, a solution for a force constant of 5919.31 newtons per meter, which is not an impossible number. It's, kind of a number that you would expect for a spring in like a suspension of a car. 5919.31 newtons per meter. So, but there you go. That's the force constant. And then that is part B.